Hello, here we have 11.6. In this section, we are going to talk about absolute convergence. So if we have a series which have both positive and negative terms, it's beneficial to distinguish between two types of convergence, absolute and conditional. So let's define what absolute convergence means. We say a series, infinite series, is absolute convergence if the series of the absolute value converges. Okay, if we have the series and when we take the absolute value of each term and it converges, we call it absolutely convergent. The second definition is opposite of it. If we have a series, it's called convergence conditionally if the series converges, but when you take absolute value, it does not converge. At that time, it diverges. So absolute value of the series diverges, but the actual series converge. We call this conditionally convergent. Okay, that also can be called not absolutely. Pay attention, this is important, that if a series has only positive terms, then absolute convergence and convergence don't have any difference, because when you take absolute value, it's not going to make any difference if all the terms are already positive. Okay, there is only meaningful distinction if there are both positive and negative terms, because if there are negative terms, you take absolute value, the negative sign goes away. But if all the terms are already positive, then it does not matter if you take absolute value or not. Okay, so here we have very important point that absolute convergence is stronger. Absolute convergence is stronger condition than conditional convergence. Why? Because absolute convergence actually claims that original series converges also. So here is an important theorem which tells me that absolute convergence is stronger. Absolute convergence is stronger. What does that mean? That if you have a series which is convergent absolutely, that means if absolute value of the series is convergent, then the original series, that implies this also is convergent. Okay, so if you can prove absolute convergence, that means you're proving the original series is also convergent. But it's not true conversely. If it is conditionally convergent, it may not be absolutely convergent, right? So let's see an example here. Show that this series converges absolutely. So if you want to talk about absolute, basically you want to test that this converges. Absolutely means you want to prove that this converges. This is our question mark. This is what we need to prove. So let's see what process I go through. I know sine theta for any theta is always lying between -1 and 1. So that means sine of n also will lie from -1 to 1. Now, n square is a positive number. So if I divide this inequality everywhere with n square, it's not going to change the inequality. So what I'm saying, sine of n divided by n square lies between -1 by n square and 1 by n square. Okay. Now, in algebra, you must have learned that if x is between negative a and a, we call that absolute value of x is less than a, right? So using that definition, we can say absolute value of sine n by n square is less than, because this is negative, this is positive, is less than 1 by n square using this algebra. So this term is less than this term. Let's talk about this series. Do we know anything about this series? What kind of series is this? This is P series with P equal to 2, which is more than 1. So this series converges. We know that, right? So sigma 1 by n square converges because it's a P series. We are saying that R series sine n by n square, that also have to converge. Why? Because of the comparison test. Both of them are positive term series. The larger series, this is large, right? Larger series converge. Larger series converge. Therefore, the smaller series, this one is small, so smaller series have to converge too. So this converges using what? Comparison test. We wanted to prove that, so we did prove what? We said the given series sine n by n square converges absolutely. What is it? Why absolutely? Because it is convergence when we have absolute value around the terms.